This lesson is going to be about pH. What pH does is it is a number that tells you how acidic or basic something is. It's based off powers of 10. So what that means is that every time the pH changes by one number, the acid concentration is going to go up or down by 10 times. All right, so to put it on a scale, what it's going to look like is, here's my number line. pH ranges from 1 to 14. pH 1 is the most acidic you need to worry about. It's when we have way more H pluses than OH minuses. That doesn't mean we have none of them. It means that they H pluses outnumber the OH minuses dramatically. pH 7 is when we are neutral, so this is 7.0 exactly, and that is when your H pluses and your OH minuses are exactly equal. And pH 14 is going to be the most basic, so again, the OH minuses outnumber the H pluses dramatically, but that does not mean that there are no H pluses. They are just very, very few of them around. Okay, so I have it represented by this, but this is not accurate. This the OH minus number here would be, hundreds of times higher than the H plus, and the reverse would be true here. Now, as far as changing of pH numbers go, here's how it works. If the pH changes from 4 to 3, we can actually say that the acid concentration, or the H plus ion concentration, increases by 10 times. Now, that is not just for 4 to 3. That is a pH change of 1. So it doesn't matter if we're going from 4 to 3, from 5 to 6, from 10 to 9, from 14 to 13. The acid concentration would increase by 10 times. Okay, that's because we changed one number. Now, if you were to go the reverse, we could say it two ways. We could say if we went from 3 to 4, we would say that the H plus ion concentration went down by 10 times. Now, the issue here is when you decrease by 10, you could also represent that as a fraction, 1 over 10, or a decimal, 0.1. So you could say that the H plus is now 1/10 of what it was, or it went down by a tenth. You could say that the H plus ion concentration is now 0.1 of what it was at 4 than it was at 3. Now, there's another way you could do this. You could also mention the OH minus concentration, because they actually do opposite things. I'm only going to talk about it once. So for OH minus, we would say that if the H plus went up by 10, it would also be fair to say that the OH minus went down by 10. Both of those statements are true. For this point on, I'm only going to define it in terms of H plus, but you could do the opposite for OH minus. And then, again, it would also be, you could now also represent it as 1/10 or 0.1. So you could do that. And the same thing with the reverse. As the H plus goes down, we could also say that the OH minus went up by 10 times. Both of those are true. Okay, so from this point on, I'm only going to talk about H plus. So if the pH changed by 2 numbers, then the H plus would increase, if it was obviously going towards 1, by 100 times, or, because 10 times 10, 10 for each number, or we would say that if we were doing the reverse, going from 7 to 9, the H plus decreases by 100 times, which could also be represented as 1 over 100 or 0.01 as a decimal. Okay, the decreases always have the fraction or the decimal option. I'm not going to talk about the OHs, but you could do that too for them. And again, this doesn't mean that specifically it's 7 to 9. It could be from 11 to 9. It could be from 9 to 7. It could be from 5 to 3. It could be from 3 to 2, as long as 2 numbers towards 1. If you move 2 numbers towards 1, that's the change that's going to happen. Or if you move 2 numbers away from 1, or vice versa towards 14, that's what would happen. If we move 3 numbers, then it would be 10 times 10 times 10. So the H plus would increase by 1,000 times. And if we move 3 numbers away from 1, the H plus would decrease by 1,000 times, or it could be represented as 1/1000th or 0.001. Okay, so you always have those options. Some vocab words, just to review: hydronium, hydroxide. Hydronium can be represented as H3O+, which is just another way of saying acid, or H+, and hydroxide, OH-. That should be reviewed. Now, I skipped over this line of the notes. I said that the H+ concentration is also represented as the negative molarity of the H+, or as the negative log of the H+ concentration. I'm going to simplify this math dramatically for you. If we look down here, here's how it works. If we look at the H+ ion concentration, let's say it was 0.1. So this was my molarity of my hydrogen ions. So if I take this number and put it into scientific notation, I get this: 1 × 10⁻⁻⁻⁻⁻, molar H+. I'm not rewriting the units. So what I would do is, if I look at the exponent tells me the pH. And it's true for every pH. So if the hydrogen ion concentration was this, then in scientific notation it would be this. The -2, I just get rid of the negative sign, and that's my pH. So this would be pH 3, and then 4, and then 5, and then you can keep going all the way up to 14. Now, the OH- concentration, you can also do that as well. That's a little bit more advanced. We are not going to get into it. All I'll say is it's the exact opposite of this, essentially. If you're doing P, technically you'd be talking about POH, but again, we're not going to mention it too much. Next page. Now, pH is important. It tells us how acidic or basic or something is, but the problem that we run into is all acids and bases are basically clear, colorless, odorless liquids for the most part. So if you think about it, you could have a glass that looks like water, and it could be pH 1. If you drink it, it'll kill you. It could be water. You drink it, you get hydrated. It could be pH 14. You drink it, it kills you. So how do you tell them apart? That's the important part. How does that work? Well, there's two ways. You can use pH meters, which are digital. They have to be calibrated. They're expensive. We don't have them, so we're not going to use them. And then the simpler and I would say probably easier method would be pH indicators. What indicators do is they change color at specific pHs. And so then based on the color that they turn when you expose them to an acid or base, you know what, you have a general pH range. It doesn't give you an exact number, but it will give you a general range. They are found on table M, and let me explain how to read it. So table M is right here, okay? And the way it works is pretty simple. It tells you that methyl orange, so there's 6 indicators you have to worry about: methyl orange, bromethymol blue, phenolphthalein, litmus, bromcresol green, and thymol blue. And then this is their color change range, and these are the colors they change. Let me explain how to read this. For methyl orange, it says 3.1 to 4.4. What that means is if it's below 3.1, it would be red. If it's above 4.4, it would be yellow. And if it's between 3.1 and 4.4, it would be a blend of red and yellow, which makes orange, hence the name methyl orange. Now, they're not all named after the middle color change, so just be aware of that. Now, bromethymol blue, below 6 is yellow, above 7.6 is blue, and in the middle, between 6.0 and 7.6, it would be green. Phenolphthalein, below 8, it's colorless, so it would look like a clear, colorless liquid like water. Above 9, it's a very intense pink. And then what do you get when you blend colorless and pink? You actually get light pink, which takes a little bit of practice to get used to, but it is light pink in the middle. Litmus, below 4.5 is red, above 8.3 is blue, and in the middle it's purple. Bromcresol, green would be below 3.8 is yellow, above 5.4 is blue, in the middle it's green, and thymol blue, below 8 is yellow, above 9.6 is blue, and in the middle it would be green. So that is how table M works. There are obviously lots more indicators than that, but those are the ones that we use in this class. So here's the way this worksheet works. I'm going to do the first 4 with you, and then I'm going to have you do the rest. So if the pH changed from 5.3, or 5 to 3, sorry, what would the hydrogen ion concentration, again, this is H+ and OH-, what would they do? And if I had this indicator in it, what color changes would I see? So it's pretty simple. Since the pH went down by 2 numbers, so it went from 5 to 4 to 3, that's 2 digits, or 2 numbers, the H+ would have a 100 times increase. The OH minus, you could also say, this is also true, would do the exact opposite. So it would have a 100 times decrease, but that's not good enough for you. I want you to give me the fraction and the decimal in each case, okay? So we'll finish these for the first 4. So 5 to 7, turns out since it's going up or away from 1 or towards 14, whichever way you want to look at it, the acid would becoming less acidic. So it would actually be a 100 times decrease followed by a fraction of 1 over 100 and a decimal of 0.01, or a 100 times increase. Okay, so it's just doing the exact opposite because it's 2 digits in the reverse direction. 7 to 10 would be going up, so we would have a 1,000 times decrease, or 1 over 1,000, 0.001. And then the other one would have a 1,000 times increase. Last one, 6 to 10, you would have a 10,000 times increase because we were becoming more acidic. And then this one would be a 10,000 times decrease, or 1/10,000th, or 0.000. To have the right number of zeros? Yes, 1. Okay, so that's the way these work. They always do opposite things. If one's going up, the other's going down, and vice versa. Now, in terms of the indicators, here's how it works. Let's look at these with table M out. So, if the pH went from 5 to 3, methyl orange would, well, let's see. At pH 5, it is going to be yellow. And then as the pH goes from 5 slowly down to 3, it's actually going to turn yellow. And if you notice, it will pass through the middle, 3.1 to 4.4. It will turn orange. And then eventually end up at 3.0, which is below 3.1, red. So now be aware, depending on the pH change, the specific numbers that we're dealing with and the indicator you're using, you don't have to have 2 color changes or 3. You could even just have no color change. It could start yellow and stay yellow. It depends on what numbers you're dealing with. And let's see how that works. So for bromethymol blue, 5 to 7, well, bromethymol blue, when it's at 5, it would be below this, so it would be yellow. And if it goes to 7, it wouldn't make it above 7.6. It would still be in the middle, so it would actually stay, it would turn green, and then it wouldn't actually get out of the green. Phenolphthalein from 7 to 10, well, phenolphthalein at 7 would be colorless, and if it goes up to 10, that means it would turn light pink, and then we'll call it dark pink or just pink, I don't care. And then the last one, litmus, if it went from 10 to 6, well, litmus at 10, it would be above 8.3, so it would be blue. And then if it went down to 6, it would cross over this line, but still be in the middle here, so it wouldn't be below 4.5. So it would be the middle color, and it would be purple. So be aware, sometimes you could have 3 color changes because you could go from one side all the way through the middle to the other side. Sometimes you could have 2 color changes, or you could have only 1 color. You could have no color changes and it could stay the same color. An example would be like, for example, if, let's just use the last one we did, litmus. Let's say I told you that litmus was at 10, so at 10 litmus would be blue, and it went to 9. Well, it's still above 8.3 in both cases, so it would just be blue the entire time and there'd be no second color. So that's how you do this. There will be a lab video on this coming out where you're going to actually take this color key or this table M, and you're going to color out the entire pH range for each indicator, and then I'll ask you questions about it. It should make this a little bit easier if this wasn't easy enough.